Today we're going to talk about enzyme catalysis. Our group members Nur Akira, Aina Zulaika, Nur Zahira, and Nur Amira.
A catalyst is a substance that provides an alternative reaction pathway which will help in speed up the reaction by lowering the activation energy compared to an uncatalyzed reaction. This does not change the frequency of collisions. However, it does increase the frequency of successful collisions because a greater proportion of collisions now exceeds this lower activation energy. Catalysis is also a substance that alters the rate of reaction. It will participate in a reaction to form an intermediate. A catalyst which is unchanged chemically will not be consumed. An enzyme is a biological catalyst which is a natural catalyst that acts as a surface that will undergo the process of reaction into producing a product. Examples for enzyme are prolytic enzymes, fat-degrading enzymes, or sugar-degrading enzymes. Model that involve for enzyme reaction is Catalysis mental model. Catalysis mental model is a model that helps in explaining velocity and mechanism of the enzyme catalyst reaction. As you can see in the picture above, substrate will combine with enzymes to form enzyme-substrate complex. As they undergo further reaction, it will be divided into two parts, which are enzymes and products. Enzymes will stay the same and wait for another reaction with different suitable substrates. Not all catalysts are enzymes, but all enzymes are surely a catalyst. Thus, make it highly thermodynamically favored. This is because of the characteristics that enzymes have. Enzymes help in speeding up the reaction and can be used multiple times using different suitable substrates. Substrates will combine with enzyme at the active site. Enzymes also will change its shape slightly as substrate binds. Then, an enzyme-substrate complex is formed. Later, the products leaving the active site of enzyme.
Macleis-Menten model. What is an enzyme activity? According to Macleis-Menten model, rate of enzymatic reaction is strongly affected by the temperature. As temperature increases, reaction rate also increases at the optimal temperature and then decreases. The Macleis-Menten model. Macleis-Menten equation is a commonly used model for enzymatic reaction because it approximates the original dynamics under the assumption that the concentration of the enzyme remains constant. And also, the enzyme interacts with the substrate to form an enzyme-substrate complex, which leads to synthesis of the product and the release of the enzyme. We assume from the Macleis-Menten model, enzyme catalyst is unchanged by duration. Second, the total concentration of enzyme is constant throughout the reaction. And lastly, production and formation is irreversible. Here are the steps that involve in an enzyme reaction, which is E plus S, enzyme plus substrate. We get ES, which is enzyme substrate complex that acts as an intermediate, and finally we get enzyme plus product, E plus product. This is the reversible formation of the enzyme substrate complex ES followed by the conversion to product. The Macleis-Menten equation. In the previous enzyme catalyzed reaction, the substrate is converted to product in the reaction that is catalyzed by an enzyme. So for many such reactions, the rate is found experimentally to follow the Macleis-Menten equation. Here the Macleis-Menten equation, V equal to Vmax times S divided by Km plus S, which is V stands for the velocity. Vmax maximum rate is an enzyme catalyzed reaction when the enzyme is saturated by the substrate, while Km Macleis constant is the measure of how easily the enzyme can be saturated by the substrate.
Next is the derivation of Macleis-Menten kinetics equation. Here is the Macleis-Menten mechanism for enzyme kinetics. The rate law for overall reaction is equals to K square times with the concentration of enzyme substrate complex. However, the enzyme substrate complex is an intermediate. Therefore, we are going to apply the steady state approximation. So we are going to say that the intermediate is equal to 0. And in this case, the D concentration ES over DT is equal to 0. So we equate the whole equation with 0. So when it is simplified and rearranged, you are going to get this expression. However, in a typical case where concentration of enzyme is not known, we are going to assume that the concentration of enzyme plus the concentration of enzyme substrate complex is equals to concentration of enzyme total, because only a little enzyme is added. So the concentration of substrate is much larger than concentration of enzyme. The concentration of substrate react with the concentration of enzyme substrate complex is approximately equals to the concentration of substrate. Therefore, when you consider the previous assumption, this is the expression you are going to get, and when simplified and rearranged, this is the expression you are going to get. So, to remove the intermediate concentration of ES complex from the rate law of the overall reaction, we are going to substitute the expression that we got previously into this rate law, where the Km in the expression is the displacement constant. Next we have Vmax. Vmax is equals to K squared times with the concentration of enzyme total. So this Vmax is actually the maximum velocity of the enzyme molasses. Alright, so what's written right now is the Michaelis-Menten equation. And the one I'm circling is the Vmax. So we can also substitute the K square multiplied with the concentration enzyme with the Vmax. Next, if we solve for the reciprocal of the Michaelis-Menten equation, we will obtain this expression, which is a Line-Weber plot.
Enzyme inhibition. Many enzyme catalyzed reactions are subject to inhibition. The rate of process is decreased by the presence of some substances. Here are the formula for degree of inhibition. I is equal to 1 minus R inhibition over R absence of inhibition. For the competitive inhibition, substrate and inhibitor compete for the enzyme active site, so they must be structurally similar. The effect of a competitive inhibitor is like decreasing concentration of substrate. Since enzyme inhibitor binding is reversible, it can be overcome by increasing concentration of substrate. For the non-competitive inhibition, because the inhibitor binds to a site distinct from the active site, it may bind either the enzyme or the enzyme substrate complex. In competitive inhibition, the value of 1 over Vmax remains unchanged with the change of concentration of inhibitor. For the reaction with non-competitive inhibition, the intercept with the horizontal axis does not move as concentration of inhibitor is increased. Since enzyme inhibitor binding is reversible, it can be overcome by increasing concentration of substrate. It doesn't matter if a product is formed from the enzyme inhibitor complex if it is not the product we are measuring. The active enzyme substrate is not affected. So, Vmax is unchanged, but the appearance of Km is increased as it takes more substrate to reach Vmax. Meanwhile, for the non-competitive inhibitor, there is no direct competition between the substrate and the inhibitor for the active site, but there is a decrease in active enzyme inhibitor concentration, so Vmax is reduced, but appearance of Km is constant.